Thank you, Nitesh, for a very generous introduction and kind introduction. I'm happy to be here. It's a wonderful place to be for this meeting. Uh, as Nitesh said, my talk is a sort of flavor of AI for science. As you all know, we are living under the AI revolution, especially last decade with deep learning, generative AI, foundation models, LLMs. Many of these terms did not exist in our vocabulary just 10, 15 years ago, right? Even 5 years ago. Uh, the other thing that you would notice, even from the presentation in this conference, is that a lot of this revolution, a lot of these technologies that you are using have been developed in the context of applications such as computer vision and language modeling and then text modeling. Uh, and of course, that'll be applied everywhere in all sorts of places. The subject of my talk is a bit, I would say, quite a bit different. Okay, uh, it is about bringing to your attention some of the challenges the humanity faces and challenges that are of existential nature. When I say existential nature, it would mean do we as a society exist 100 years from now, a couple of hundred years from now, or maybe even a few decades from now, will be impacted. Right? So these are very serious challenges. That's one part. Second part is so second component is how the AI revolution that has changed everything in our life, everything literally, right? How could it help in addressing those challenges? The third part is because these challenges are so unique, uh, require advances in AI of a very different nature that you have seen so far. Okay, and KGML, the guided machine learning, is sort of a theme in that direction. That is, it's a machine learning that's underpinned by scientific knowledge, and why that is the case, you will sort of hear about that in a little bit. And then lastly, what I want to impress upon you is young people like you in the audience, the students, the masters and bachelor's and PhD students, to show you their work in being able to not only advance the state of the art in AI by coming up with new formulations, but also moving the state of the art on addressing some of these environmental challenges on a global scale. So sort of very humbling that yes, our field has come this far in 7 years in the field of AI, that we could really make an impact at that scale. And lastly, if I have some time at the end, I would conclude with sort of a history of the field over a period of last 7 decades, how it has sort of flowed over this period, what are the different themes that have happened, and how the science could be the driver of AI revolution going forward into the future. With that, now, I should also warn you, there'll be portions of this talk that might look very foreign to you in the sense that because they'll be talking about scientific problems, so they'll be a little bit technical. I've tried to minimize that. So if something doesn't sort of hit your head, don't worry. The next slide would be easier to understand, right? I have to sort of go through a few things here, but the overall message is sort of what is that yes, there is a capacity, there is a potential in this community to be able to address some of the biggest challenges that are facing the humanity, and in the process, advance our field. Okay. So with that, let me sort of see what are those challenges. And of course, one you have heard almost every day from the newspapers, from TV, and from what goes around you, right? Is climate change. Yeah, that is we all know the climate is changing. Humans have been putting in too much of the greenhouse gases into the atmosphere. We are at record high. We got to stop this, right? And even already we're seeing increasing frequency of droughts and floods, fires where the forests exist, and hurricanes who are becoming very intense. And here's the kicker: even though we all know, being understood the problem, that eventually we'll have to get to net zero. I think the path, how do you get to there, is a difficult question, but we know we'll be getting there. But the thing is, even if tomorrow we got to net zero, that somebody magically woke up tomorrow and we're not emitting any greenhouse gases. We've already logged in whatever warming we have for thousands of years. These gases stay in the atmosphere for a very, very long time, right? Every year we wait makes things worse, right? Now, here's the next kicker. That is, climate change is only one of the problems. Okay? There are many, many other problems that are facing us as a humanity that are of existential nature, that are all interconnected. Okay? And, and again, these are important because people like me won't have to worry about it after a few decades, but a lot of you who are young people would be living through it, right? So for younger people in the audience, you have to sort of listen carefully and say, hey, look, this is my future, that I have to worry about, right? So the second challenge is about how do we feed the growing population of the world really destroying its biodiversity? And just to give you a sense of what's happening here is that in year 2000, about 24 years ago, the population of the Earth was 6 billion. Today, we are about 8.2 billion. So about 30%, 35% increase in just 24 years. Right? If you go back 100 years, we have increased the population of the Earth by a factor of 4, right? 2 billion to about 8.5 billion. Right? Now, if you have more to feed, what do? You need more land for agriculture, right? So humanity has grown over the last 10,000, has always been cutting more and more forest to more agriculture. And what you're seeing in this picture on the top right corner is a very large area in Indonesia. On the right side is very dense old growth forests that are very high density carbons. And just to the next of it is you have oil palm plantations that, because the forest has been cut, the plantations have been placed there, and the oil palm that comes out of is being used by every one of us. You go home, you look at the pantry, you pick up any item there, and if it has a list of ingredients, it'll have oil palm in it, right? For the most part. So what I'm saying, these forests are being deforested in Indonesia. Every one of us is contributing to it. So I'm not trying to point fingers at one country, right? But the fact is, we are rapidly deforesting, and we're losing the biodiversity on the Earth, and the biodiversity is what sustains us. And there are so connections. I could give an hour-long lecture on it just by itself. It's a very, very serious problem. It's an existential problem. That means even if you solve the climate change problem somehow, the biodiversity problem still stays. And of course they interconnect. The second thing is, if we got to feed more mouths, what do? We intensify agriculture. So 100 years ago, people hardly used any fertilizers. Today, everywhere in the world, you use fertilizers to increase the production of the crop. The crop production actually has gone up many-fold over the last many decades, right? Now, what happens when you put fertilizers? Of course, your crop yield goes up, but a lot of that fertilizers then washes and goes into your lakes and the rivers and into the ocean. Okay? And that sort of creates a big problem in the short term and in the long term. Okay? Short term, because you got to drink water. Okay? The long term, if oceans have a lot of nitrates, not of these fertilizers, the life in ocean would die. Of course, life in ocean dies, the whole planet dies. In the sense, there'll be no life on the planet. Right? So there are problems multiple scales here. Now, the last item I'm going to touch upon is the agriculture. But of course, we need agriculture so we can eat ourselves, right? We got to produce food. And the production of food emits about almost 25% of the total greenhouse gases into the atmosphere. Right? So, of course, if you build electric cars, you can reduce the emission from the transportation. But you got to eat food, and agriculture is producing so much emission because why? Because of the fertilizer that we use. They intensify agriculture, they increase yield, but they also are highly potent warming gases that they can actually warm up the atmosphere like 20, 30, 40 times more than the CO2. So there are many such interactions. The other thing is there's a lot of carbon that is stored in the soil of Earth. When we do agriculture, when we grow food, a lot of that carbon comes out. So the amount of carbon in the soil is actually very large. If you reduce by a few percentage, we could solve the carbon. We could solve the greenhouse emission problem or make a big dent into it. So how do you figure out ways to grow food? And more importantly, how do you figure out ways to incentivize farmer to change their practices to grow food so that more carbon can stay in the soil, less carbon is emitted, so that we can feed the people, we can keep our waterways safe, we don't have to cut so many trees, and we can solve the the climate change problem. So this is sort of gives you sort of a spectrum of environmental challenges. This is not the entirety of it, but these are some of the biggest challenges. And they are all at the intersection, the nexus of food, energy, water. We need food, we need energy, we need water, and then they're all sort of interconnected into this in this shape. So there are, this is for the most part, people here are data scientists, computer scientists, and try to say, why are we talking about? Because there are a large number of scientific communities who are studying these questions. How do we answer these, solve these problems, right? And those questions would look like these. And don't worry if you don't understand what these questions are, but how do we understand the global carbon cycle? What's happening in the atmosphere? It's like, if you put certain amount of carbon, how much does the earth get warm, right? How do you understand the modeling the climate system? How do you get net zero? What are the different ways you sort of get to a zero carbon economy? How do you make the economy or the society resilient to increasing number of droughts and floods that are happening? How do you improve your modeling of the droughts and floods, right? How do you mitigate the water pollution in our lakes and waterways so that they can be healthier? And how do you make the agriculture sustainable and zero carbon and of course also feed? So all sorts of questions. They are some of the most prominent questions, right? So that society, this scientific society, is beginning to sort of study, right? And how do they study them? How do they study them? Unlike our community, which sort of says data, and I'll build a model, right? These communities, scientific communities, over decades and centuries, the sort of the tradition in this is over literally hundreds of years engineering environment. Like unlike in data science, you give me the data and I'll try to figure out, build a model. Maybe my model will tell you this, right? They try to build a model, right? And what they do is that to build a model, the environmental system that you to study. Of course, in this case, you're trying to be perhaps a lake or a riverway, maybe an agricultural farm. You're trying to figure out what is impacting it. For the great part, like the physical weather, the temperature, the pressure, the precipitation, all sorts of things like that. You may be interested in the flow of the river, like how much water is flowing through a river in response to precipitation. You may be interested in knowing the temperature of a lake because that is a major driver of its health. You may be interested in figuring out how much greenhouse gas is being emitted, from a farm because you are trying to figure out what practices would reduce it, right? And so forth. This is a system is driven by something which there's a response that you're interested in, and the relationship between these drivers and response is governed by some underlying characteristic, like what is the quality of what is the land cover, how you're managing it, and so forth. Again, this is several technicality you may not want to bother about, but this is basically the system that they're trying to model, right? And with the ability of sensors over the last many decades, sensor revolution, we're able to also watch these environment systems on a very varied scale. You can fly drones to watch your farms, but you can also see them from the sky. The Earth observing satellites have a completely wall-to-wall coverage of the entire Earth, at a very resolution, right? So you have this is a system they sort of try to model. This is IIT Jodhpur. It is a department of any southern computer science. You walk into somebody or the other is a model framework like this, right? And the two caricatures that I'm showing you on the bottom right, bottom left, are one for hydrology, in which you're trying to model hydrology of a basin in which the rain would fall. Some of the water would get absorbed by the soil, some of it would get evaporated by trees, and some of it will go into the river. Eventually, this modeling, it would sort of tell you whether the floods are going to be caused or the floods are going to be happening, or the lakes, in which you're trying to figure out the dynamics of its temperature and its quality. in response to all of the other things. So people would build these forward models. These are called process-based forward models. These will have scientific equations. Those are the kinds of things you would study. Mechanical engineer, fluid dynamics, environmental engineer. You will go to university for 4 years or probably school and do PhD, trying to understand how to build these models and what are the soil cycle, what is the water cycle, what is the how they interact with each other, put into equations and then build these models. This is exactly how the weather works, right? You open your app and you see what's the temperature in Jodhpur tomorrow in the evening. The app is getting data from a model which is literally running as an indicator of what I talked about. So this frame is used in literally every scientific discipline. So the forward models, which says I'm trying to figure out what the response is in response to the drivers. Could be inverse, which sort of says, well, I know the drivers and the response. Can I understand the system by underneath? So there are all sorts of things. This long history, long tradition of building these models in these scientific communities, right? Now the question is, why are we talking about them? Haven't the people solved problem of modeling this environmental system already, right? Well, we have the models, we have the problem, and we just give the policymakers the right solutions and directions for them to act, right? The problem is that anytime you're trying to build any model of a real system, you have to do approximation. It's never possible to be able to make a perfect model, right? You have to make approximations. Partly either you don't know the underlying physics, or even if you knew the physics, you can emulate it at the right temporal and spatial scale, right? Again, this may be a bit of technicality for you, but just take it that every scientific would sort of say, yes, yeah, I can do the model, but really, my model is not perfect, right? For the most part. Oftentimes, in nearly all the cases, the models will have parameters. And just to give you a sense of parameters, this will be the level of hydrology I'll do in this 2 minutes. Let's say you're trying to figure out in your hydrology model, if the rain falls, how much of it goes and gets into the soil, right? Well, it depends on how absorbent the soil is. If you go out in Jodhpur, half a mile from here, it's all sandy. The rain falls and it goes into this sand. Nothing will flow, right? The soil has a lot of capacity to absorb water. If you go and in the middle of Jodhpur city, it's concrete. Most of the places, there's the street, the water falls, it flows sideways, right? So the amount water the soil can absorb depends of soil can have different layers, and different layers could be able to model the absorbent capacity of soil at every different level. And of course, if you do that, you have one layer parameter. If you have 10 layers, you have 10 parameters. The model becomes more precise, but it needs more parameters, right? But then how do you find the values of those parameters? Well, then you have to have some observations for the rainfall and the flow, so you can sort of calibrate those parameters. This is a term called calibration, which means you're looking for the values of those parameters that'll give you the best match between the observations and what you're predicting, right? Okay. So parameters, but much more importantly, you need a lot of observations to be able to handle them. And even more importantly, what happens is that if you have a place which you're trying to model, and you have placed a lot of sensors, and you have built a very good calibrated model, now if you go to a different place, you go from Jodhpur to Jaisalmer, suddenly you need new values for parameters. And that is one of the biggest drawbacks of this traditional scientific methodology. They make very inefficient use of the observation, even though they make effective use of the physics that we have learned decades and such, right? So this has caused, these limitations have caused literally every scientific community in the world look towards what we are doing, what you are doing in community in advancing the frontiers of AI. Everybody is sort of saying, hey, look, maybe what these guys are doing, it will apply to us too, right? 20 years ago, there was hardly any scientific community that paid attention to what's being done in this group. Today, every single scientific community is looking at AI to solve their problem, right? So basically, given that AI and ML have revolutionized all aspects of our life, they're increasingly considered as alternative to the traditional time, okay? Of course, you see that with ChatGPT, shook people up. Look, if ChatGPT do such a good job, maybe there's something, right? But also see the 2 Nobel Prizes that were awarded in physics and chemistry, right? And I just want to warn people that, look, this is interest in AI in the scientific community, not new. It's not within the last 2 years. The 2 covers showing you for Nature and Science. These are the sort of the highest journal, the most prominent journals in the science and scientific community. These 2 covers are not from the last 2 years. Can anybody guess how far back do they go? It's 15 years ago, right? So what I'm trying to say is that it's not like just up today. There have been interest in this area, right? And National Science Foundation in the US launched this Harnessing the Data Revolution program about 10 years ago. So you can sort of see that people were thinking about it. But the interest has become so much more intense. There's so much interest, and there's so many more capabilities that every major corporation, every scientific community is paying attention to it. Already, some of the best weather forecasting you get today in the short term is coming from the machine learning paradigm, foundation models. Again, just to give you a sense, right? Okay. So now the question is, you might sort of say, hey, look, AI has arrived. We got a lot of data. Why can't we forget all what these engineers and scientists were doing for decades and centuries? Well, just say you go home. And that is not necessarily a completely wild thought. We have done that for the linguists. Linguists have been trying to understanding of language for 7 decades. When I was a graduate student in the 70s, 50 years ago, the language translation was one of the hardest things, right? People were trying to model it as grammars. Today, you can take your phone and point at any text, pretty good translation, right? And the translator uses jilts from what has been done in the scientific community in the computational linguistics, right? So people say, well, why can't we do it here? Here's the problem. These methods that we have built and that have shown so much success require a lot of data, but these are very complex models. Okay? Now, that's one part. The other part is that these models have no understanding of underlying physical phenomena, which can create results that are inconsistent with physics. Okay? What that means is that if you are being result inconsistent scenario with physics, they will not be able to generalize scenarios unseen. So in foundation models, in the LLMs, it reflects itself as hallucinations, right? So they're creating things that really just don't exist, right? That are not even possible, right? And the other thing is that if you got very good predictive understanding, you're not really using science. We have very, very good made good progress in language translation. Field of linguistics has not advanced at all. They are still moving along at the same rate. And the line that is much more critical is that all of the advances that we are doing in AI are driven by the internet. For the most part, are driven by the internet. They're trying to make sure that you click on the right ad and buy the product, right? If they send you 100 and you click on one of them, they make more, right? So their prediction doesn't have to be good, okay? But here, dealing with things that have consequences of life and death, right? So you can't simply say, hey, look, I have a prediction which is better than random. You got to have something that's usable, right? So these sequences of missing a flood warning can be far more serious than missing a recommendation that happens to be wrong. So, and the reason I sort of, these have to be stated is that there is a segment in our community who's beginning to think that maybe we don't need scientific theory, right? I'm showing you some of these snippets from 2008. End of theory, data deluge makes methods obsolete, right? Or more recently, we're witnessing the dawn of a post-theory. So you don't need any theory. You just work with what you have. So all I'm just trying to say that, yes, look at this left side. There's a big caution there. And you can see failures, spectacular happen in older time and more recent times from Google and Meta, where things can really fall apart completely. And so we can really simply say, rely upon the data. Right? So where are we now? So we have this dichotomy. We have the traditional scientific paradigm, which relies upon mathematical equations to model the scientific world that you're trying to model. Okay? processes, underlying processes, how they interact, and so forth. And they make limited use of data. And then we have this very powerful, recent models, especially, that do particularly well when you have a lot of data, okay? But they fail to generalize or give you inconsistent results when the data is not representative or data is not enough, right? So both of these incomplete use are two sources of information that we have. So this knowledge, the topic of knowledge-guided machine learning is about mining both of these. That's why skip any of them? Okay, that is, why not? Why not basically build machine learning models that can actually combine the power of science, all the knowledge that has been accumulated? Why throw it there, right? And again, this is a paradigm that is evolving over last years. Some of the original papers, I'm listing some of the original papers. A lot of them mentioned as physics-guided machine learning or physics-informed machine learning. But basically, the knowledge-guided machine learning means that you can have knowledge of any kind beyond physics. It's a very rapidly growing community. There are workshops and surveys, papers, funding calls on KGML. There are books and articles, and every single discipline you can imagine is using this methodology. There are papers published every day. Yeah, and I'll show you some of the advances made, in pushing the frontiers. These sort of slides are coming from a tutorial that was sort of presented at this workshop that held at Minnesota just a few months ago. And if you go to the barcode here, you'll see the entire workshop, the tutorial, and learn all about this different dimensions of this paradigm and how you combine scientific knowledge with machine learning. I won't have time to go through this, just to sort of show that there are different formats of representation of knowledge in terms of PDEs or scientific laws or symmetries or graphs. You heard graphs this morning too, or mechanistic model types of scientific knowledge. Could be perfect or complete or imperfect form of knowledge integration and so forth. And this presentation that you will go see to the workshop, you will learn a lot more about different concepts of this, which I'm going to sort of ignore here, given the short of time. I just want to sort of tell you that by combining scientific knowledge and machine learning, the advances that we've been making over the last 10 years, I should say 70 years, it has the potential to provide highly predictive power with very few observations, generalized to scenarios not seen before in ways that was never possible before, produce physically consistent results, and much more importantly, the biggest problem that we have with the scientific models, that is, if you train them in one place with a lot of data, and you go to a different place, again, you need the data, right? And the power here is that you can leverage the information from places you have data to go to other places where you have very little data, very few observations, by methodologies like zero-shot and few-shot learning, by making them informed by scientific knowledge. So this is sort of, if I had to give a 2-minute talk, just like everybody else giving, just before my talk, I would just show a slide and say, hey, look, come back to my poster, right? Okay. So now what I'm going to show you in a rapid succession, some results on some very the significant results, because they push this sort of the art beyond what anybody could have done in this study. That's number one. Number two, just to remind you, those results obtained by people like you, right? They were different, but just like the ones in the art here, right? So I'm just giving you this results. This is, of course, a few years old, but it's in the top cytology journal, number one. And number two, this was the first demonstration of the fact, yes, you can combine scientific knowledge with machine learning to leapfrog both of these methods. So what I'm showing you here is the ability to model the dynamics of temperature of lakes. There are 185,000 lakes in the United States. There's an entire agency called United Geological Surveys, whose responsibility is to monitor the health of the lakes. And temperature is a master variable. These are the guys who sort of work with us, the chief of modeling at the agency. So what you're seeing here is that if you use the traditional method for modeling GLM, which is the process-based model, it's in operational sense. Basically, if you have more observations, do better calibration, and your error RMSE goes down. If you go up, the error goes down. The green curve is going up, right? If you have purely machine learning model, a standard LSTM. If you have very little, there's a lot of error, but if you have a lot of data, the error becomes smaller, even smaller than the best process model. For this lake that I'm showing you results, we happen to, it's the widely observed lake in the world, so it has a lot of data. Actually, you can exceed the process model. But if you combine the power of both, you can actually work with very few data points and get very, very good results. And of course, eventually, it's very, very efficient in getting those right. Okay. Now, much more importantly, this sort of shows, well, if you give me data, I'll give you a good model. But what happens in scenarios unseen? There were many different sort of scenarios were tested. They published this top hydrology journal, which sort of shows, again, I'm going to keep this story short here, that two scenarios on the left and right. The left scenario is one in which the training came from the general setting. 30 years of data, take portions of years for training, other portions for testing. On the right side, what you do in training years, you never show them the data for the summer. In the testing year, everybody's tested on the summer, right? So what you see here is even the green model, the process-based model, drops performance because it doesn't know, it has not calibrated its parameters for the summer. The orange model, the black machine learning model, black model, drops like a rock. It doesn't know anything about summer. That's expected, right? This model that is guided by science and data really drops very little, even though it also hasn't seen anything about the summer. Right? This was actually the first demonstration, people say, of showing the sample generalization extrapolation way that could not have been done before. But much more importantly, this amount of, okay, so next one is really showing you that you could sort of show that energy can be conserved by this physical model. Now, to tell you a little bit more detail, it'll take me a lot more time. Just to save time, what I'm just going to remind you is that the two curves here, the blue and green, one of them is the curve for how much is the net energy gain of the lake, and the other curve is saying how did the temperature of the lake go up or down. If these energy is conserved, those two curves should match. Okay? So for the lowest curve, ELM process model, those two curves match. For the top curve, which is a plain machine learning, it doesn't match. The middle one, because it's the knowledge-guided machine learning, it sort of matches very, very well. Okay? This is another thing. You can go out of sample, you can conserve energy. And the last one is actually very important. I mentioned to you, there are situations we have a lot of data in some places to calibrate, but as you go out to a different scenario, you learn from scratch. And this is where being able to extrapolate from regions which are observed, the green portions of this matrix, to areas like pink, where you're looking at entities that are completely different in different time, is the biggest challenge. And this is where the KGML really, really shines. And I'm just going to give you one example of this, which is, again, a result made possible by KGML. There are 185,000 lakes in the US. The data exists only for 10,000 lakes, 12,000 lakes. For the remaining lake, there is no data. How do you know what's happening there? Learning cannot do anything, and the process models cannot calibrate early, so the results are, people don't consider the results, good. So this methodology is to build the first time a record of temperature dynamics of all of these lakes that was accepted by the community because of the quality of the result we were able to show at work. Again, this was done by a PhD student, Jared Willard, in my lab, and of course the jointly with United States Geological Service, and again, a remarkable stone for the community, right? So the entire agency has adopted KGML as their mission, as part of their water mission, because of this success, right? Another example here, a completely different one. I mentioned to you about being able to head to the zero economy, which means you got to figure out what parts of the Earth are emitting how much carbon. Now, the one way to figure out how much carbon is being emitted in part of the world is to play these tower called eddy covariance towers. If you put this tower, they are sort of looking at the wind, they're measuring all the different air that's flowing through it, and they can measure a lot of things, including the amount of greenhouse gases, right? So there are a couple of hundred places in the world, the dots, a lot of them in North America, in Europe, and other parts of the world, where are collecting data, right? But then how do you find out what's happening in the places where there is no such tower? right? So then this methodology was shown to sort of work in this setting in the following sense. Well, we have about a couple of hundred where we have this eddy coherence tower. We're going to hide a bunch of them from the system. We're going to build this KGML model from the remaining one, right? And I'm going to make prediction on the remaining places without looking at what the this is predicting. And results came out that if you bring in plain machine learning, the errors would be high and you would need a lot of data. Whereas if you use this knowledge-guided machine learning, which is the last row of this column, with very few observations, it can actually give you as much quality as with a lot of data, and of course with more data, everybody, right? So this is another example of how you could sort of take data from highly observed cells and take it to less observed cells. Another example here, this is with the agents in the United States that does forecasting, and these are the people who would go onto the TV every day and sort of make forecast for what you're going to see next. And there are about 13 operational forecasting centers in the United States, and one of them happens to be the one in Chanhassen, Minnesota, which is responsible for making forecasts for about 5 different states. Each state, there are, for the region, there are like hydrologists, each responsible for a small region of this year. And they basically use process-guided models, and they're trying to figure out what forecast should give on the TV. They know what has happened until today, but what happened tomorrow, day after, if the flood is coming in, what could happen 7 days from now, and so forth, right? So what you here on this curve on the bottom left is this stars. So I'm looking at a 0 time today, but since I have looked in the back, I know what will happen to the future. So it starts sort of telling me the value of the high river 7 days into the future, 6 hours, right? If you use a standard process model or a machine learning, it will be the red curve, which is actually off. If you use the blue curve, you're also using the knowledge of what has happened in the past. Still pretty off. Now, if you use this knowledge-guided machine learning framework, I haven't told you what it is about, but it's a pretty sophisticated work, which is the blue curve. You can see that starting at time 0, you're able to make predictions of what would happen to the river flow all the way up to as much as several days in advance, in this case, 7 days in advance. So these are some of the advances made possible because you're able to model using machine learning what are the different processes inside these hydrological systems, how they're interacting with each other. And the last example I would give is this one of being able to model the greenhouse gas cycling from agriculture. It's a huge issue in the sense that in the entire world, we'll have to practices that are not emitting carbon, and especially in the there's a huge focus on being able to turn agriculture from net emitter of carbon to net negative on carbon. And the way you do that is by being able to figure out what management practices give you how much greenhouse gas emission. And again, people have these process-based models, which are not very good by themselves. You use pretty learning models. They are not very good by themselves. But if you combine them, and again, caricature on the top right is sort of trying to show, or bottom right is trying to show that this model of KGML actually can do a very good job, much better job than anything else available. This is a very recent work, and there's a huge we have at Minnesota, funded by National Science Foundation, AI Institute, which is focusing on advances like these. Okay, this is again, I mentioned earlier the foundation models, similar to large language models, are the rage now in scientific community. A lot of potential for using them in every single problem. And again, there are a number of foundation models that are being developed right now for the geospatial data. And this is sort of just an example of how these models, if they're combining the scientific knowledge, how much better they can be. And I'll just show you just one example here that you look at this picture here, you're given, this model is given these pictures up to this point, and then it's asked to make, this is up to this point, and it's asked to make prediction of what will happen 120 days into the future. Now, this is the ground truth. This is what plain foundation model on machine learning would do, and this is what, if you bring in the scientific knowledge, and you can sort of see the green part, which was white before, it sort of transitions into green 120 days later, using this KGML model. And of course, the plain machine learning model can sort of get to it. And this green part became hardened here or became snow, the ground truth, but also was picked up by knowledge-guided model. So what I'm trying to say is that the amount of improvement you could do, the power of these algorithms is very, very high if you bring the scientific knowledge. So with conclusion, I just want to sort of, this was a rapid fire introduction to how AI can really advance. But this slide is sort of try to remind you that the way AI is talked about today is not the same AI that people talked about multiple decades ago, right? There are many, many threats that fed into what we see beyond in the last 12 years. So look at the very last column on this picture on the slide, okay? See all of the most recent advances. 2012 AlexNet wins ImageNet challenge, and then you see underneath the technology that went into it. What was the technology? CNN built 23 years ago was used for that, right? ImageNet just a couple of years ago was used for that, right? Google translates quantum jump, self-supervised word-to-vec function at least half a dozen times in the couple of hours before. 2016, the computers became champions on Go. 2018, the AlphaFold, protein folding, big advance in science, right? Again, that sort of really brought attention of the scientific community to the power of AI. What was driving that? Transformers, just from a year ago, okay? 2017, okay? Attention is all you need, right? 2019, there was a 20-year roadmap for AI created by National Science Foundation and Community Consortium, which actually did not even mention the transformer. Not aware of it. I mean, this group was the best and the brightest, right? You know, of everybody, and I was there in the middle of it, and he went back to the report. There was no mention of transformer. So this, you can sort of see how parochial we can be. Today, we don't know what happened in the last year. Be the shining light tomorrow, right? And of course, 22 ChatGPT came in, and 2024, 2 years later, everybody doing generative AI. And how am I saying that? Half ago, almost 2 years ago, NSF asked me to hold at their headquarters this workshop on AI-enabled scientific revolution. That was March, and Nitesh was there, right? He held one of the most important panels there. And we barely talked about ChatGPT there, right? Mostly in the predictive term, right? And then 6 months ago, or I guess 5 months ago, we held the second version of this work in Minnesota, and every single talk was about AI. So this is how much scientific community has changed, right? So last column tells you there's a rapid pace of progress. It's breakneck pace. It's almost like exponential, right? And oftentimes we don't know what's happening, right? You know, what has just happened. But what has happened here is not just what you're seeing. It's fed by streams coming in from the past, right? And in the other, I'm showing you multiple streams. And one of the stream is in the middle one, right? Which is sort of more the history of this conference. If you look at the conference, look at the paper, they come in the middle stream. This focus on the 90s to 2012 was about being able to solve practical problems. Big data was, right? You got to be able to adapt your problems to big things, right? Decision trees, rule-based systems, ensemble methods, subtraction machines, Bayesian network, they all came in during this time. They were in by the commercial applications, commerce, web, and actually web wouldn't enable without these advances, right? They were also driven by the scientific applications. You know, the Sloan Sky Survey created images. The high-throughput revolution in biology created a lot of data, and so forth. Protein prediction actually was back to the late 80s. As the problem, of course, really got solved very recently. And to drive the point, just to tell you how clueless we can be, you know, at time as to what's coming into the future. In 2012, President Obama launched a White House Big Data Initiative. Okay? And if you go back to the web and you look at Okay, so this is happened here. But then things were happening before 1990s, right? So the AI, the term AI that we're using today, right? Everybody's using AI term today. Everybody's doing AI. It was coined in the 60s, right? And it was in 60s in the symbolic AI, right? That is to mimic human intelligence. Okay. If you take the AI 101 class, I'm sure you people about A star, and things like that. Problem solving search, planning, decision making, right? Narrative AI, logic programming, procedural AI, expert systems. If you went to AI conference in the 80s and 90s, there'll be panels and there'll be people debating heavily about is declarative AI the way to go and procedural AI the way to go, right? Okay. Again, a lot of that is sort of cited, although if you look through some of the advances that were made in this column, many of them would not have been possible without the rooting back to the earliest time, right? Because if you look at the reinforcement learning, it played a key role in many of the demonstrations on the last column, and reinforcement RL basically goes back directly to search and planning, right? So there's a very, very direct connection there. But then there was this third thread, which actually started at the very beginning in the 60s, made its head up and then got shot down and made its head back up in the 80s, got shot down. And then it came back in 2012 vengeance, and which is the neural networks, right? So 1957 perceptron, the basics of what you're doing today, the basic foundation is with perceptron. I can make my model learn by making little changes in the weights, okay? But at that time, I realized, well, you can solve problems that are so simple, I could use regression for it, right? Then in 1974, somebody doing a PhD in mathematics at Harvard University, Paul Verbose, came up with backpropagation algorithm, but nobody understood it. Okay? Then in 1986, Hinton and the company came up with, reinvented the backpropagation. They did not steal it, they just reinvented it. And they sort of said, hey, good. And suddenly they became very famous for a couple of years. And then it subsided because it was too complicated, even though they are universal approximator. CNN was invented in 89, at the heel of that time, right? 97, LSTM was invented. I'm sure nobody heard about it or talked about it until, of course, 2012, a series of happening, right? So what I'm saying is that there are multiple threads, multiple streams fed the revolution today. For anyone to think that only the neural network got us here, it's a complete failure, because it's the big data thread got us the ImageNet, right? And there's one more thread that I'm missing here, which is the computer vision and pattern community, which was actually kicked out in 1970 out of the AI group by saying, hey, you're not focusing on making human intelligence, you're focusing too much on the problem. So they were kicked out. The conferences on pattern recognition and computer vision were separate out of the AI in 1970. And those are the guys who brought the whole back, right? So basically, here are these different threads, different rivers flowing in, but what we're in the middle of is actually very exciting revolution. And I expect that many more of ideas from different threads enrich us, and this ability to bring in scientific knowledge would actually be really key to making the next advances. So with that, I'm just going to leave you with this view that most recent advances in AI are driven by vision and language modeling. I mentioned that earlier. But the next revolution in AI driven, this is sort of my hypothesis, my statement, would be a much wider class of scientific domains, because each scientific domain brings its interesting challenges. And KGML is one such advance that has the potential to address some of the biggest advances and biggest challenges in society, but also biggest gaps in AI, like trustworthiness, accessibility, and fairness that of course are being talked about at this meeting extensively. So let me just thank my collaborators and my students and the agency that have been funding this work. And thank you for your attention. And I'm happy to take any questions if there's any. Yes. Oops, okay.
Thanks. It was very nice talk. So two questions. One is, I think you briefly referred to there is the whole field about symbolic AI, right? So pretty much the same applied to scientific data. So that is one. And if you could say a little bit about the specific techniques of how do you combine those, maybe right when you go deep down, when you said really coming from the symbolic side, and what are the specific models that you
Okay, so I think it's a very valid question. I often get asked. So I think the question is, if I understood you correctly, that is the knowledge-guided machine learning same as bringing sim AI to the machine learning framework? And it's a similar thought, but a completely different one. The reason is the following: the symbolic AI in all of the time, we were never paying attention to the scientific field. We are never paying attention to the laws of conservation or the actual model processes, right? But it's a different kind of knowledge. And I think there is a potential to bring the symbolic information into the learning framework. And you could say the knowledge graphs are a way to do that. Like it's like when people try to bring in knowledge graphs in the machine learning, it's almost like taking the symbolic information, bringing into the ML framework. I would call that symbolic AI integration into the traditional ML yet another path. I mean, the KGML path is all about bringing scientific knowledge, but it doesn't preclude other kinds of knowledge to be included. So there are multiple threads that I have to sort of bring in. And my hypothesis is that because the nature of the scientific problems is so different and the knowledge that they have is so critical and so important, bringing them into the framework can really dramatically improve the performance. Next question.
Uh, Thank you, Vipin, for the great talk. I think Parag covered the question I wanted to ask. So just on top of it, where do you exactly use the knowledge? Does it go in the creation of the neural network? I think papers like K-BAN, right? They are as old as 1994, where knowledge was used to design the architecture. Or do we use knowledge to create some sort of labels for training the neural network? Where exactly is this knowledge going?
Perfect. Like I said, I rushed through the slides because I wasn't sure how much time I would have. So I gave you multiple dimensions, and this dimension is talking about what are the different ways of bringing knowledge into the machine learning framework, right? So one of the simplest method that works for everybody, and again, you'll see in 90% of the papers, the thousands of papers published on this theme right now, is just simply modifying the loss function. You bring in the loss term that comes from violating any scientific law, right? Which is the first in the row, right? You're changing the shape of the thing. But some of the biggest advances have come from the middle part. That is, you change the architecture, which is exactly what you're saying. And here's the kicker. If you take this lens into the history, you could sort of say CNN is a knowledge-guided architecture. LSTM is a knowledge-guided architecture, right? And basically, Jan LeCun was sort of saying, how do humans think? How do humans see it? Well, this concept of having the filters, right? It was inspired by what he saw. And of course, the human functioning of human brain was inspired of people. David Marr, if some of you sort of know, his work was very influential, right? So also trying to do the same thing, but eventually CNN really hit it in a way. It changed the field, right? LSTM is doing something very similar in a sequence of time, right? So if I sort of bring in the KGML, I would sort of say, look, it actually goes back to Jan LeCun. He was the first guy who thought about it. Then there are guys who invented LSTM, right? And of course, the more recent ones, right? Basically, if I am bringing in scientific knowledge of vision, CNN is the first KGML model. We're bringing in the knowledge of the languages, the sequences. LSTM is the second KGML model. Also, we have a whole series of models now. Yes, exactly. But those biases are informed by how much we know about the physics. I showed you about this method that gives you prediction 7 days in advance, very accurately, which basically brought in the inductive bias by saying there are multiple processes that are happening inside this basin, and they're interacting at different scales. And just bringing that bias brought us to that point. So it's the more you bring in, the better it works. So what it allows you to do is not only leverage data, but also the deep understanding of the science to work together.
So this last slide was mind-boggling. I almost felt like I just got a course done on fantastic. Looking at this evolution of ML, so to speak, one of the things that came to my mind, that the very basic ones, when you talk about the loss function and what, right? People had some lever on it. Like they knew that if I do this, my result would get this much worse with certain guarantees. When this simplicity evolved and things became more complex, like new architecture, or even now a sequence like this foundational model does, what happens to these simple guarantees? Where do we go from here? Are we just trying to go to a place where things are experimental, and if it works, it works? If it doesn't work, we don't know why it doesn't.
God is on our, we just to the God, right? So this is actually the question that hounds other scientific communities a lot more than we pay attention to it. Why? Because these guys are into being able to make prediction using whatever physical they have. So they will always put uncertainty quantification. So if you put climate modeler, they will say, hey, look, Earth is going to warm if you double the carbon. If you double the carbon into the atmosphere, Earth is going to warm by 3 degrees. But then they say, no, the band is 1.5 to 4.5, 3 is in the middle, right? And of course, depending on how good your models are, the band would become wider or smaller, right? So they tell you, when we held this workshop 5 months ago, one of the biggest question that was that these LLMs, they're generating information, right? Mm-hmm. But do they know what they don't know?
What they don't know.
See, if I ask you a question about, let's say, hydrology, let's say you're not a hydrologist, you will sort of say, hey, look, I'll give you an answer, but don't trust my answer because I don't know anything about hydrology. But the LLM will give you an answer, right? So the ability to bring in understanding of what you know or what you don't know is sorely lacking, right? As a community, we haven't paid much attention to it. Community models inherently are very, very bad at it. Generative models are much better at it, but the traditional generative model. But the current ones actually are completely ignoring it, right? So I think some of the biggest advances, as I said, one of these young students in the audience, right? Or somewhere on, right, would come up with methodologies.
Sure.
That would sort of get us there. But that's one of the hardest questions that people should be thinking about, although not enough people are thinking about right now. But as I give my talk, that is one question that always comes.
Thank you.
Yes.
Thank you. That's very insightful.
Take it from you and then take the mic.
Yeah. So I had a question. So when we talk about climate modeling, right? So this is a process modeling. So
Yes.
What is its relationship to causal AI?
Wonderful. See, if you are only given data, right, you got to figure out the cause and effect, right? If I see people using umbrellas, right, it doesn't mean that if I take people's umbrellas away, it won't rain, right? Because traditional data-driven models look for associations, right? Even prediction is association, right? It doesn't tell you causation. So if you only have data, you got to figure out what's causing what. And again, the entire framework developed by Pearl and going back deals with that. But the scientific community actually works the other way. They build a causal model. The entire model they built is causal. So every one of the questions that Pearl's asked, right? Can you do, can you figure out what if questions? Of course, if you trust your model, you can answer everything because it's the carbon that's warming the temperature, right? It's the water eventually that flows into the river. If there's no rain, there'll be no flood, right? It's not the flood causing the rain, it's the rain causing the flood, right? So things like that. So the process models are inherently causal. The only thing is they're not perfect models. Right? They're approximation of reality. So this is where the marriage of the two can get us closer, having a causal understanding and having a good prediction.
Yeah, I have a question in context of physics-inspired networks. I think just a couple of minutes ago you mentioned the use of custom loss functions. Custom loss functions to minimize.
Yes. I put that here.
Right. But I think there are certain things that you cannot. For instance, mass energy momentum balances. You cannot penalize. You cannot put them in the. They have to be adhered to no matter what. You cannot put them in the another term in, it's your approach might be okay, fine, put it in, put a penalty term, etc. But the right way to doing that is perhaps include them as constraints in the operation framework. But then that challenge the existing paradigm. Any comments on that?
Perfect question. Perfect question. So let me repeat the question, right? Okay, that's a wonderful question. And these are the kind of thinking that has to go in, right? Okay. So the point is, hey, look, if you believe the energy to be conserved, right? And if you put into the loss function, right? It's a soft constraint, right? In the sense that it's going to try, but it's also trying to look for prediction, right? The energy conservation should be iron, it should be like iron fist. It should not be violated, right? Okay. So the right way to do it would be to put in the architecture. And I can show you a paper in which we have sort of taken the constraint and put it into the architecture. And of course, then it's guaranteed to be there, right? Okay. But for the result I showed you in which the energy was conserved was actually using the loss function. And you would sort of say, hello, Vipin, why did you do that? Now, let me give you the answer. So the energy that is being conserved, we are watching it by looking at the sun's reflection into the lake, observed by the satellite. And the temperature change in the lake, we are observing by the sensor. The two different things, they never match, in the sense that you could never have perfect match between the two. So here is what happened, actually, because we were in the early stages when we did this thing. We were not even thinking about the architecture. We were thinking only about the loss function. So what happened was we put this constraint, right, in the loss function, and we trained it to the hills, and performance became much worse. Why? Because the measure of information actually was inaccurate. So it had to be made less accurate. So sort of say, if the energy balance is within delta, ignore it. If it's more than that, then complain and you get it done. And it did a pretty good job. And then of course, it improved the performance for that. So you have to sort of see what knowledge you can bring in and how do you bring it in. And what this is sort of showing you, there are multiple ways of doing it. And one of these young minds will think of a different ways of doing it for a different problem. Yes. Yes.
One final question there.
Thank you so much, sir, for the wonderful talk. So my question is, you was talking about science, AI for science, and in computer science itself, we have theoreticians. They come up with theoretical algorithms, and then when they don't scale up, when you don't have guarantees, come up with heuristic algorithms. And heuristics come from theory, come from the model, come from the domain. So where do they figure in this whole picture?
Okay, what you're saying is the how do you bring in the correctness, right, into the game, right? Okay. So I would say that I am dealing with correctness from a narrow angle of science, right? Which means all the other questions that computer scientists, we as a computer scientist have to study, still exist. You know what I'm saying? They all exist, they're all very important, and they all have to be made progress on. But what I'm trying to say here is that if you keep building machine learning models to solve problems the way we have been doing in this community, then we're leaving a whole bunch of information on the table. And by leaving it on the table, we are actually producing suboptimal, perhaps dangerous results, in the sense they may fail in ways that would be pathetic, and we could prevent it. Right? So what I'm talking about does not invalidate any of the other lines. Actually, they're equally important. It's just that here is a line that we would have never thought about. So we're dealing with the scientific problems. But great question.
All right, thank you all so very much for your engagement and an exciting set of Q&A. And let's thank Professor Kumar again, please. Thank you. And then as we all have witnessed before, we have a couple of tokens of appreciation for Professor Kumar. One, a tree has been planted in your name, sir, by ACM, at ACM India, at the 14 Keys Foundation in Pune. So now you have to make a trip to Pune to water your tree.
Wonderful. I will do that.
For you.
All right. Thank you.
And this is another token of appreciation from the organizing committee.
Thank you.
Thank you very much.
Thank you. tethered to.
They can back it up with that.
Oh, okay. That's very nice. Next session starts. I'm going to get out, right? Okay.
So,
Oh, sorry.